Hello everyone, I'm going to go over how to do the problems from the quiz, in case you're retaking the quiz. So, question number 1 for the 10th grade quiz asks you, please write the following numbers as their prime factorization. First of all, you should know that the prime numbers that we need to check for prime factorization are 2, 3, 5, 7, 11, 13, 17, and 19. Just these prime numbers could be the factors for the questions on the quiz. How do we check if a number has a prime factor? We just divide the number by one of these factors in C. Obviously, 4,235 is not even. So let's not start with number 2, because there's no way number 2 could be a factor of this number. Instead, let's start with 5. So I make a tree, I write 5, and now I use my calculator and I divide 4,235 divided by 5, and I get 847. Now I try a different prime factor, obviously not 5, because it doesn't end in 5 or 0. Let me try 7, 847 divided by 7. Oh, it does work. So I write 7 and 121. Now for 121, I'm going to try 13. 121 divided by 13. It doesn't work. Let me try 11. So 121 equals 11 times 11. So then I copy my answer down here. 5 times 7 times 11 squared, because there are two number 11s. So my final answer is 5 times 7 times 11 squared. Let me try one more time with 672. I'll write it a little bigger this time. 672 ends in 2, so it must be divisible by 2. I divide it by 2 and I get 336. 336 ends in 6, so it must be divisible by 2. I get 2 times 168. 8 is divisible by 2, so 168 must be divisible by 2. I get 84. 84 ends in 2, so it must be divisible, ends in 4, so it must be divisible by 2. 84 divided by 2 is 42. 42 ends in 2, so it must be divisible by 2. 42 divided by 2 equals 21. 21 is 3 times 7. This is just a fact that I've memorized. Now I count how many 2's? 5 2's. So 2 to the 5th power times 3 times 7. And that's how I factor into prime numbers. Question 2 asks us to finish the table to find the best estimate of phi, which is the Fibonacci number. To find or estimate phi, we have to continue the Fibonacci sequence. 1 plus 1 equals 2. 1 plus 2 equals 3. 2 plus 3 equals 5. 3 plus 5 equals 8. 8 plus 5 equals 13. 13 plus 8 equals 21. 21 plus 13 equals 34. How do I get the number on the bottom? 1 is 1. 1 divided by 1 is 1. 2 divided by 1 is 2. 3 divided by 2 is 1.5. 5 divided by 3. You can see 2 divided by 1, 3 divided by 2. 5 divided by 3 is 1.6 repeating. 8 divided by 5 is 1.6. 13 divided by 8. I think it's 1.625. 21 divided by 13. Let me use my calculator. 21 divided by 13. I'm going to take 1, 2, 3 digits. 1.615. 34 divided by 21. 1.619. And I have finished my estimates for phi, the Fibonacci number. Phi is an irrational number as well. We can never know its exact value. We can only estimate it with bigger and bigger fractions. Number 3 asks us, which of the following numbers are rational and which of them are irrational? Rational means you can write the number as a over b, a fraction. Irrational means we cannot write a over b. A and b are numbers like 1, 2, -2, 500, 3, whole numbers basically. 1.3 is rational because 1.3 equals 13 over 10. 0.55555 is rational because it equals 5 over 9. Square root of 2 is not rational. It's irrational. Why is too complicated to explain for the quiz. However, you should memorize this is one of the most important irrational numbers. E is irrational. It's a very special number. We won't use it in class yet, but you should know it's one of the most famous numbers in mathematics. Pi is irrational. It's when we divide the circumference of a circle by its diameter. That seems like it would be a fraction, a over b, but it'll never be whole numbers, so it's irrational. We have to memorize that pi is irrational. Square root of 4 equals 2, and 2 equals 2 over 1. It's definitely rational. R, I, R, 50 is rational. Why? Because we can write it as 50 over 1. And I just said that phi or phi is irrational. This is something that you have to memorize. It's important to know, even though you might not understand why it's irrational yet. Question 4 asks us to organize these 5 sets of numbers, not the examples, into a Venn diagram. Many people think a Venn diagram has to look like 2 circles that are overlapping like this. This is just one example of a Venn diagram, but it's not what our Venn diagram will look like today. Instead, our Venn diagram will start with a circle that has the naturals. And the naturals belong to the integers. This means all natural numbers are integers, but not all integers are natural numbers. For example, -3 is an integer, but it's not a natural number. 2 is a natural number and also an integer. The integers belong to the rationals. These are numbers that we can write as fractions. Rational is the opposite of irrational. It will sit outside. A number cannot be rational and irrational at the same time. Just like the sun cannot be in the sky and below the horizon at the same time. It has to be one or the other. Finally, all of these numbers are real numbers. All of them are real. This means there are some numbers that are not real, but we're not going to talk about those numbers in our class this year. Just so you know, those numbers include things like complex numbers, as well as ideas like quaternions. And these are important if you ever plan on studying math in the future as an engineer or a scientist, or perhaps a data analyst. All right, here it asks us to turn the following repeating numbers into fractions. A lot of students did a great job using algebra to turn these numbers into fractions. However, we can also use a symbolic approach. Let's say x is a number like 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. X over 9 equals 0.xxx forever. X over 90, we add an extra 0, equals 0.0xxx forever. Xy over 99 equals 0.xy forever. And x over 10 equals 0.x. Let's use these rules to convert these decimals into fractions. I'm going to do the first one. 0.4355 dot dot dot. We have that x over 10 equals 0.x. So we could say this number equals 0.4 plus 0.03. When the 4 is gone, it becomes a 0, plus 0.00555 forever. These two zeros are where the 4 and the 3 were before we separated them. We know x over 10 equals 0.x. So 0.4 becomes 4 over 10, according to this symbolic rule. If we add a 0 under the fraction, we're also adding a 0 to the right of the point. So we have 0.03 equals 3 over 100, because now we've added an extra 0. Finally, we have two zeros and one repeating number. So this becomes 5 over 900. We're not done yet. We need to get one fraction out of this answer. So we equalize the denominators. 4 over 10, how can we get that to be over 900? We multiply 4 times 90, and it becomes 360 over 900. How can we get 100 to become 900? We multiply this fraction by 9, and we get 27 over 900. And this is already over 900. So we just add across, and we get 392 over 900. All I did was add 360 plus 27 plus 5 to get 392. This fraction is not in its simplest form, but we don't need to put it in the simplest form for the quiz because that's not one of the ideas that we covered in class, and it's not relevant to the lesson. A lot of students circled the correct prime numbers, or some of the correct prime numbers in this question. However, they didn't show their work for how they find the prime numbers. To use the sieve of Eratosthenes, which is the oldest way of searching for prime numbers, we start with the smallest prime number, which is 2. We cross out all the multiples of 2. So multiples of 2 end in 0, 2, 4, 6, and 8. So I cross out first all the numbers ending in 0, 2, 4, 6, 8. So now I've done 2. The next smallest prime number is 3. I look for the first factor of 3, which in this case is 231, because 231 divided by 77 equals 3. I cross out and then I count. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 1, 2, 3, 1, 2, 3, 1, 2, 3. It's a little boring. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Now we've done 3. We have to move on to 5. 5 is easy because all numbers divisible by 5 end in 5 or 0. 5, 0. We move on to 7. As the prime numbers that we're checking get bigger, we're going to have fewer and fewer multiples of them. For 7, we have to look for the first number that's divisible by 7. So I'm going to use my calculator and check. Can I divide 230 by 7? No. Can I divide 231 by 7? Yes, I can. This is the first multiple of 7. So I count from here. 0, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. All right. The next smallest prime number is 11. I know for a fact that 231 is a multiple of 11. So I'm going to start counting from here. 231, 242 plus 11, 253 plus 11, 264 plus 11, 275 plus 11. We've already left the numbers on the field. Now we have to check for 13 and 17. The reason that we stop at 17 is because 17 times 17 equals 289, and it's already larger than the largest number on our list. For 13, I'm going to start with the multiple of 13 that I know off the top of my head, which is 260. I go back 13 and cross out 247. I go forward and I cross out 273. That's it. There's no more. We already crossed out 234. Finally, for 17, I know 289 is a multiple of 17. So I go 289 minus 17 equals 272. 272 minus 17 equals 255. 255 minus 17 equals 238. There's no more numbers to check. Now I circle the numbers that are left over. If I did my sieve correctly, all of these must be prime numbers.